Imagine reaching Mars in just 2 weeks. Right now, the vast majority of space travel, from launching satellites into orbit to sending probes to distant planets, relies on chemical rockets. These systems operate on a fundamental principle: ejecting mass at high velocity to generate thrust, a concept rooted in Newton's third law of motion. Chemical propellants are ignited and expelled, creating the force that propels spacecraft. They are the workhorse of space exploration and have been instrumental in every major achievement, from the Apollo moon landings to the deployment of the James Webb Space Telescope. However, as we set our sights on more ambitious destinations like Mars and beyond, the inherent limitations of chemical propulsion become glaringly apparent. One of the most significant drawbacks is their inefficiency. Chemical rockets consume enormous amounts of fuel, and the more fuel you carry, the heavier your spacecraft becomes, which in turn requires even more fuel to accelerate. This creates a tyranny of the rocket equation, a fundamental challenge that severely restricts payload capacity and achievable speeds for long-duration missions. For instance, a one-way trip to Mars using current chemical rocket technology typically takes between 6 and 9 months. A round trip, accounting for planetary alignment for the return journey, could extend to 2 or 3 years. This extended travel time presents significant challenges for human missions, including increased radiation exposure for astronauts, the need for vast quantities of consumables like food, water, and oxygen, and the psychological toll of prolonged confinement in a small spacecraft. Despite these limitations, current space exploration is a vibrant and active field. Numerous robotic missions are continuously expanding our understanding of the solar system. For example, NASA's Perseverance rover and China's Tianwen-1 mission are actively exploring Mars, while the UAE's Hope orbiter studies the Martian atmosphere. The Europa Clipper mission is en route to Jupiter's moon Europa to investigate its potential for life, and the Psyche spacecraft is traveling to a metal asteroid of the same name. Nearer to home, the International Space Station, ISS, continues to host astronauts for long-duration research, and the Artemis program aims to return humans to the moon, with a goal of establishing a base camp there by 2025 as a stepping stone for future Mars missions. Private companies like SpaceX are also playing an increasingly significant role, developing advanced rockets like Starship, which Elon Musk aims to use for a maiden flight to Mars by late 2026. While these endeavors push the boundaries of what's possible with existing technology, the desire for faster, more efficient, and more sustainable space travel is driving the development of next-generation propulsion systems. The current state of space travel, while impressive, is still largely confined by the speeds achievable with chemical rockets. Even the fastest spacecraft to date, the Parker Solar Probe, which reached speeds of 430,000 miles per hour during a solar flyby, would still take several days to reach Mars at its closest approach, and tens of thousands of years to reach the nearest star system, Proxima Centauri. This stark reality underscores the urgent need for revolutionary breakthroughs in propulsion technology. The current approach, while effective for shorter distances within our solar system, simply isn't viable for truly exploring the vastness of space or establishing a sustainable human presence beyond Earth orbit. The dream of interstellar travel, or even significantly reducing transit times to Mars, remains largely out of reach with our current capabilities. The limitations of current space travel are stark when we consider ambitions beyond Earth's immediate vicinity. Chemical rockets, the workhorse of space travel since its inception, rely on expelling hot gases to generate thrust. While effective for launching from Earth and initial boosts, their efficiency is fundamentally limited by the rocket equation. This equation dictates that an exponential increase in fuel is required for a linear increase in velocity, making missions beyond our solar system incredibly challenging with existing technology. Typical speeds for interplanetary travel with chemical propulsion range from 12 to 24 kilometers per second, approximately 28,000 to 54,000 miles per hour. Even with gravity assists, like those used by the Voyager probes which achieved around 17 kilometers per second, these speeds translate to immense travel times. Consider the journey to Mars, our nearest planetary neighbor. An ideal alignment between Earth and Mars, known as a launch window, occurs only every 26 months. Even with this optimal alignment, a trip to Mars typically takes about 9 months using current propulsion methods. While some concepts, like SpaceX's Starship, aim to reduce this to as little as 80 to 100 days, these are still substantial durations. When we look further out into our solar system, the numbers become even more daunting. A trip to Jupiter, for instance, can take several years. For Saturn, it's longer still. These protracted travel times pose significant challenges, not just from an engineering perspective, but also for the human element of space exploration. Long-duration missions expose astronauts to a range of physiological and psychological stressors. Microgravity, for example, leads to a decrease in bone density at a rate of about 1.5 to 2% per month in weight-bearing bones, and muscle atrophy, particularly in the lower extremities, can result in a 20 to 30% decrease in muscle mass after 6 months. The cardiovascular system is also affected, with fluid shifts, reduced plasma volume, and a decrease in cardiac muscle mass due to reduced workload. Upon returning to Earth, astronauts often experience orthostatic intolerance, making it difficult to stand for extended periods. Beyond the physical, the psychological toll of prolonged isolation and confinement in a cramped spacecraft cannot be overstated. Astronauts can experience mood swings, anxiety, depression, sleep disturbances, and even cognitive decline. The lack of privacy, social deprivation, and the stress of being far from family and social support can lead to significant mental health issues and interpersonal challenges among crew members. These psychological factors can jeopardize mission success, as evidenced by historical missions where crew depression was a contributing factor to early aborts. Furthermore, the deep space environment presents the constant threat of radiation. On Earth, our atmosphere and magnetic field shield us from harmful cosmic rays. In space, astronauts are exposed to much higher levels of radiation, which can damage DNA, weaken the immune system, and increase the risk of cancer. This radiation exposure could lead to serious long-term health problems and is a critical concern for missions beyond Earth's protective sphere. These physiological and psychological hurdles necessitate extensive countermeasures, including rigorous exercise regimens, nutritional supplementation, and psychological support. But even with these, significant gaps remain in fully mitigating the risks for deep space missions. The sheer distances involved also have profound economic implications. The more time a mission takes, the more resources are consumed, from life support and provisions to the operational costs of maintaining a crew and spacecraft for extended periods. This exponential increase in resource requirements with longer travel times makes ambitious missions incredibly expensive. The rocket equation, as mentioned earlier, means that carrying more fuel to go faster makes the rocket heavier, requiring even more fuel, creating a vicious cycle that significantly drives up costs. While reusable rocket technology is helping to reduce launch costs, the fundamental challenge of interplanetary transit times remains. The dream of interstellar travel, reaching beyond our solar system to other stars, remains firmly in the realm of science fiction with current technology. Proxima Centauri, the closest star to Earth, is approximately 4.25 light-years away, or about 25 trillion miles. The fastest spacecraft ever, the Parker Solar Probe, reaches speeds of up to 450,000 miles per hour during its solar flybys. While incredibly fast, at that speed, it would still take the probe about 6,633 years to reach Proxima Centauri. This stark reality underscores the critical need for a revolution in propulsion technology. We need to travel faster, not just to make interstellar dreams a reality, but to truly unlock the potential of our own solar system, to establish a sustainable human presence beyond Earth, and to conduct meaningful scientific exploration that isn't limited by decades-long transit times. The current pace of space travel, while a testament to human ingenuity, simply isn't fast enough to meet our aspirations for exploration and expansion. The current pace of space travel, while a testament to human ingenuity, simply isn't fast enough to meet our aspirations for exploration and expansion. This is where advanced propulsion systems like nuclear thermal propulsion, or NTP, come into play. NTP is a revolutionary concept that promises to dramatically cut down transit times for deep space missions, making destinations like Mars not just reachable, but routinely accessible within a human lifetime. At its core, nuclear thermal propulsion operates on a principle similar to conventional rockets, but with a critical difference: the heat source. Instead of relying on chemical combustion to generate hot exhaust gases, an NTP system uses a nuclear reactor. Imagine a liquid propellant, typically hydrogen due to its low molecular weight, being pumped through the core of a nuclear reactor. Inside this core, uranium atoms undergo fission, splitting apart and releasing an immense amount of heat. This heat is then directly transferred to the liquid hydrogen, rapidly heating it to extreme temperatures and transforming it into a high-pressure gas. This superheated gas then expands and is expelled through a rocket nozzle at high velocity, generating thrust and propelling the spacecraft forward. The key advantage of this approach lies in its efficiency, specifically what engineers refer to as specific impulse. Specific impulse is a measure of how much thrust you get from a given amount of propellant, essentially the fuel efficiency of a rocket engine. Chemical rockets, which burn propellants like liquid hydrogen and liquid oxygen, typically achieve a specific impulse of around 450 seconds. In contrast, nuclear thermal rockets are designed to achieve specific impulses of 900 seconds or more, effectively doubling the propellant efficiency. This dramatic increase in efficiency is primarily due to the use of hydrogen as the propellant. When chemical rockets burn, they produce heavier byproducts like water vapor. Hydrogen, being the lightest element, can be accelerated to much higher velocities for the same amount of energy input, leading to a greater specific impulse and allowing the rocket to travel farther on less fuel. This means a nuclear thermal rocket can deliver a greater payload mass into space with less propellant or achieve faster transfers to orbit, significantly minimizing travel time to a destination. For instance, a trip to Mars could be reduced by as much as 25%, cutting down a 9-month journey to just 3 to 4 months. This reduction in travel time is particularly crucial for crewed missions, as it limits astronauts' exposure to harmful cosmic radiation and the physiological effects of prolonged microgravity. The concept of nuclear thermal propulsion isn't new. It has a rich history dating back to the 1950s. The United States, through programs like Project Rover and NERVA, Nuclear Engine for Rocket Vehicle Applications, conducted extensive research and ground testing of nuclear thermal engines from 1955 to 1973. During this period, more than 10 reactors of varying power outputs were built and tested, accumulating over 17 hours of engine runtime. The NERVA program, in particular, achieved significant successes, developing powerful engines that were several times more efficient than their chemical counterparts. For example, the NERVA NRX achieved a specific impulse of 825 seconds using hydrogen propellant, and the Phoebus 2A reactor generated over 4,000 megawatts of thermal power, making it the most powerful nuclear propulsion reactor of its era. These programs demonstrated key capabilities such as high-temperature carbide-based nuclear fuels, a wide range of thrust levels, sustained engine operation, accumulated lifetime at full power, and restart capability, all essential for a human mission to Mars. However, the U.S. program was eventually shut down in 1973 due largely to budget constraints and a shift in focus towards the Space Shuttle program. Despite these early successes, no nuclear thermal rocket has yet flown in space. Current research and development in nuclear thermal propulsion are experiencing a resurgence, driven by renewed interest in deep space exploration. Organizations like NASA and the Department of Energy are actively collaborating on research, development, and the anticipated demonstration of functional nuclear thermal rockets. The U.S. Congress approved significant development funding for nuclear thermal propulsion rockets in 2019, and DARPA, Defense Advanced Research Projects Agency, has been pursuing its demonstration rocket for Agile Cislunar Operations (DRACO) program, although its planned orbital demonstration was recently put on hold. The European Space Agency also proposed its own NTP engine, called Alumni, in June 2025. There are several types of nuclear thermal rocket designs, categorized primarily by the state of matter of the nuclear fuel within the reactor: solid core, liquid core, and gas core. The most developed and simplest type is the solid core nuclear thermal rocket. In this design, the nuclear fuel, typically uranium-235, is contained within solid fuel elements. Liquid hydrogen propellant is pumped through channels in these solid fuel elements, where it absorbs heat directly from the fission reactions. The NERVA program primarily focused on solid core designs, using graphite matrix fuel elements containing uranium carbide. Modern solid core designs are also exploring the use of high-assay low-enriched uranium, HALEU, as fuel. While solid core NTRs are significantly more efficient than chemical rockets, their maximum operating temperature is limited by the melting point of the solid fuel and cladding materials. Beyond solid core designs, researchers are exploring more advanced concepts like liquid core and gas core nuclear thermal rockets, which promise even higher efficiencies. A liquid core engine, for instance, would operate at temperatures above the melting point of solid nuclear fuel, with the fuel in a molten state. This could potentially deliver specific impulse performance in the range of 1,300 to 1,500 seconds. However, building a liquid core reactor presents significant technological challenges, such as managing the much longer reaction time of the nuclear fuel compared to the heating time of the working fluid. Gas core nuclear thermal rockets take this a step further, where the nuclear fuel is in a gaseous or even plasma state. There are two main varieties: closed cycle and open cycle gas core NTRs. The closed cycle, sometimes called a nuclear light bulb, contains the gaseous fuel in a transparent vessel, preventing it from mixing with the propellant. The open cycle gas core, where the fuel is a charged plasma held in magnetic fields, could achieve even higher temperatures because the gas doesn't physically touch anything. However, a major challenge with open cycle designs is preventing the fission products and unburned fuel from being swept away with the exhaust, which would make the exhaust highly radioactive. Another advanced concept being researched is the centrifugal nuclear thermal rocket, which uses molten uranium within a rapidly spinning centrifuge, allowing hydrogen propellant to bubble directly through the liquid fuel and absorb extreme heat. This approach could nearly double the efficiency of current solid core systems. Despite the immense potential, nuclear thermal propulsion faces several challenges. One of the primary hurdles is the weight of the reactor and the necessary radiation shielding, which can lead to poorer thrust-to-weight ratios compared to chemical rockets. This makes nuclear engines less feasible for launch vehicles that require very high thrust-to-weight ratios for liftoff from Earth. Therefore, NTP systems are envisioned for use in space, launched into orbit by traditional chemical rockets, and only activated once safely away from Earth. Another significant challenge is the extreme heat generated by the nuclear fission reaction, which places stringent demands on the materials used in the reactor core and cooling systems. Maintaining the structural integrity of fuel rods at temperatures of around 4,400 degrees Fahrenheit is a complex engineering feat. Furthermore, the radioactive nature of nuclear reactors presents safety and environmental concerns, particularly regarding testing and potential accidents. Ground testing of nuclear thermal engines requires specialized closed facilities with exhaust capture systems to prevent radioactive contamination. Historically, open-air testing was conducted, but modern environmental and safety regulations demand far more sophisticated infrastructure. A catastrophic failure of a launch vehicle carrying an unactivated nuclear reactor could scatter radioactive material, and even during operation, the reactor itself is highly radioactive, bombarding surrounding spacecraft structures with neutrons and gamma rays, which can induce radioactivity in the spacecraft itself. Despite these challenges, the advantages of nuclear thermal propulsion are compelling. The ability to achieve significantly higher specific impulse, reduce transit times to distant destinations, and carry greater payloads makes NTP an enabling technology for ambitious deep space missions, particularly crewed journeys to Mars and beyond. The ongoing research and development, building on decades of foundational work, suggests that nuclear thermal propulsion could soon move from concept to reality, ushering in a new era of faster, more efficient space exploration. While nuclear thermal propulsion offers a significant leap forward, another powerful contender in the realm of advanced space propulsion is nuclear electric propulsion, or NEP. This technology, distinct from its thermal counterpart, harnesses nuclear energy to generate electricity, which then powers an electric thruster. Unlike the direct heating and expulsion of propellant seen in NTP, NEP separates the energy source from the propulsion mechanism, offering unique advantages and engineering challenges. At its core, NEP systems utilize a nuclear reactor, typically a compact fission reactor, to produce heat. This heat is then converted into electrical energy through a power conversion system, much like a terrestrial nuclear power plant, but on a much smaller and more robust scale designed for the harsh environment of space. Technologies like Brayton cycles, thermoelectric converters, or Stirling engines are all under consideration for efficiently transforming thermal energy into electrical power. The electricity generated is then fed into an electric propulsion system, such as an ion thruster or a Hall effect thruster. Ion thrusters, a well-established form of electric propulsion, work by ionizing a propellant gas, typically xenon, and then accelerating these ions to extremely high velocities using electric fields. The expulsion of these high-speed ions generates thrust. Hall effect thrusters operate on a similar principle, using a magnetic field to confine electrons, which then ionize the propellant and accelerate the resulting ions. Both types of thrusters are characterized by their incredibly high specific impulse, a measure of propellant efficiency, meaning they can generate thrust for a very long time with a relatively small amount of propellant. This is a crucial advantage for deep space missions where propellant mass is a significant constraint. The primary advantage of NEP lies in this high specific impulse. While the thrust levels produced by electric thrusters are generally much lower than those of chemical rockets or even NTP systems, they can operate continuously for months or even years. This sustained, low-thrust acceleration allows a spacecraft to gradually build up immense velocities over time, ultimately reaching much higher speeds than would be possible with high-thrust, short-burn systems. Imagine a gentle, persistent push that, over an interplanetary journey, translates into a phenomenal burst of speed. This continuous acceleration drastically reduces transit times for robotic probes and, crucially, for crewed missions to distant destinations. For instance, a mission to Mars using NEP could potentially cut transit times by several months compared to conventional chemical propulsion, significantly reducing astronaut exposure to radiation and the psychological stresses of long-duration spaceflight. The power levels required for effective NEP systems are substantial. Current state-of-the-art electric propulsion systems, like those used on commercial satellites, operate in the kilowatt range. For deep space human exploration, however, NEP systems would need to generate megawatts of electrical power, a 1,000-fold increase. This leap in power generation presents significant engineering hurdles. Developing compact, lightweight, and highly reliable nuclear reactors capable of sustained megawatt-level operation in space is a monumental task. These reactors must be designed to withstand the vibrations of launch, the vacuum of space, and extreme temperature variations, all while operating autonomously for extended periods. Furthermore, the power conversion system must be equally robust and efficient. Minimizing heat rejection is critical in space, as radiators are heavy and bulky. Therefore, maximizing the efficiency of converting heat into electricity directly reduces the size and mass of the required radiators. Advanced materials and innovative thermodynamic cycles are being explored to achieve these efficiencies. Another significant challenge is the integration of the nuclear reactor with the electric thrusters. The sheer amount of electrical power generated by the reactor needs to be efficiently transmitted to the thrusters, often over considerable distances within the spacecraft. This requires advanced power management and distribution systems capable of handling high voltages and currents while minimizing power loss. The radiation environment created by the nuclear reactor also necessitates careful shielding to protect sensitive electronics and, in the case of crewed missions, the astronauts themselves. This shielding adds mass, which must be carefully balanced against the performance benefits of the system. Despite these challenges, the potential rewards of NEP are immense. Beyond faster transit times, NEP offers unparalleled flexibility for mission profiles. The ability to generate continuous thrust means spacecraft can perform complex orbital maneuvers, rendezvous with multiple celestial bodies, and even carry larger payloads due to the reduced propellant mass fraction. For ambitious missions to the outer planets or even the heliopause, NEP could be a game-changer, enabling scientific investigations that are currently beyond our reach. Consider a mission to Jupiter's moon Europa, a prime candidate for harboring extraterrestrial life. With conventional propulsion, the journey is long and the payload mass limited. An NEP-powered spacecraft, however, could reach Europa faster, carry more sophisticated scientific instruments, and even have the capability to perform multiple flybys or enter a stable orbit around the moon, significantly enhancing our understanding of this enigmatic world. Similarly, for human missions to Mars, NEP could not only shorten the journey, but also provide ample power for habitats, life support systems, and scientific equipment once on the Martian surface. The abundant electrical power could even facilitate in-situ resource utilization, such as extracting oxygen from the Martian atmosphere or water ice, further reducing the reliance on Earth-supplied resources. The development of NEP builds upon decades of research in both nuclear power and electric propulsion. Early concepts for nuclear electric rockets emerged in the mid-20th century, and the fundamental principles have been validated through numerous ground tests and orbital demonstrations of smaller-scale electric propulsion systems. Agencies like NASA have been actively pursuing NEP concepts for human exploration, recognizing its transformative potential. Projects like the kilopower reactor concept aim to demonstrate compact fission power systems suitable for space applications, laying the groundwork for future NEP missions. The ongoing advancements in materials science, power electronics, and reactor design are steadily bringing NEP closer to reality, promising a future where our reach into the cosmos is no longer limited by the constraints of chemical rockets. While nuclear electric propulsion represents a significant step forward, The quest for even faster and more efficient space travel leads us to explore the fascinating realm of plasma propulsion. Plasma, often referred to as the fourth state of matter, is an ionized gas consisting of free electrons and positively charged ions. Unlike NEP, which primarily uses electricity to accelerate ions, plasma propulsion leverages both electric and magnetic fields to generate thrust by expelling this superheated, electrically charged gas at incredibly high velocities. The fundamental advantage of plasma propulsion lies in its significantly higher specific impulse compared to traditional chemical rockets. Specific impulse is a measure of how efficiently a rocket uses its propellant, and plasma engines can achieve specific impulses several times greater than chemical rockets, meaning they require far less propellant for a given mission. This translates to lighter spacecraft, reduced launch mass, and the ability to undertake longer missions with higher payloads. While the thrust produced by plasma engines is generally much lower than chemical rockets, they can operate continuously for extended periods, gradually accelerating a spacecraft to much higher speeds over time. This makes them ideal for deep space missions where sustained, efficient acceleration is paramount. Several types of plasma propulsion systems are currently under development and even in limited operation. Two of the most well-known and practically applied are ion thrusters and Hall thrusters. Ion thrusters generate thrust by accelerating ions using an electric field. They are highly efficient and have been successfully used in missions like NASA's Dawn spacecraft. Hall thrusters, a subset of ion propulsion, utilize magnetic fields to confine electrons, which then ionize the propellant. Both systems provide gradual but constant acceleration, allowing spacecraft to reach high velocities over extended durations. One remarkable example of a Hall thruster is the X-3, developed by the University of Michigan in collaboration with NASA and the U.S. Air Force. This nested-channel Hall thruster shattered previous records for maximum power output, thrust, and operating current. The X-3 demonstrated a total power throttling range of 2 to 200 kilowatts and achieved a record-breaking 5.4 newtons of thrust, more than doubling the previous record for a Hall thruster. Its ability to operate efficiently on both krypton and xenon propellants, along with its wide throttling capability, 1,600 to 3,200 seconds specific impulse with xenon, makes it a strong candidate for high-power missions, including human exploration of Mars. Researchers believe that Hall thrusters like the X-3 can be optimized for either carrying equipment with minimal energy and propellant over a year or for rapidly transporting a crew to Mars. Beyond ion and Hall thrusters, other advanced plasma propulsion concepts are being actively researched, pushing the boundaries of what's possible. The Variable Specific Impulse Magnetoplasma Rocket, or VASIMR, is a prominent example. Conceived by former astronaut Franklin Chang Diaz, VASIMR utilizes radio waves to ionize a propellant, typically a low molecular weight gas like helium or argon, into a plasma. A magnetic field then confines and shapes this plasma, and further radio frequency, RF, waves heat the ions to extremely high temperatures, on the order of 1 million Kelvin, before expelling them at velocities up to 70,000 meters per second through a magnetic nozzle, generating thrust. One of the key advantages of VASIMR is its constant power throttling capability, allowing in-flight optimization of thrust and specific impulse to reduce trip times. Proponents suggest a 200 megawatt VASIMR engine could drastically cut travel times, potentially reducing a trip to Mars from 6 months to just 39 days, and a journey to Jupiter or Saturn from 6 years to 14 months. The electrodeless design of VASIMR also contributes to its potential for high power density and extended component life by mitigating plasma erosion. Another intriguing concept is the pulsed plasma rocket, PPR, derived from the pulsed fission fusion concept. The PPR is designed to generate substantial thrust, potentially up to 100,000 newtons, with a high specific impulse of 5,000 seconds. This combination of high thrust and high specific impulse could revolutionize space exploration by enabling manned missions to Mars in as little as 2 months, significantly reducing crew exposure to radiation due to faster transit times. Research also continues into magnetoplasmodynamic (MPD) thrusters, which use the Lorentz force generated by the interaction of an electric current and a magnetic field to accelerate plasma. While MPD thrusters have been researched since the 1960s, they have not yet been used operationally in space. However, recent tests by NASA's Jet Propulsion Laboratory, JPL, with an experimental lithium-powered MPD thruster achieved unprecedented power levels in the United States for this type of system, reaching up to 120 kilowatts. Scientists believe lithium-fed MPD engines, paired with nuclear power systems, could play a crucial role in future deep space exploration by combining strong thrust with efficient propellant use, allowing for heavier payloads on human Mars missions. While the promise of plasma propulsion is immense, several challenges need to be addressed before these technologies can be fully realized for widespread deep space missions. One of the most significant hurdles is the substantial power requirement. Plasma engines need a lot of electrical power to operate effectively, and generating this power in space, especially for missions far from the sun where solar panels are less efficient, remains a major engineering challenge. Miniaturization of high-power plasma thrusters with high impulse and efficiency is also a critical need. Another key challenge is the relatively low thrust produced by most plasma engines compared to chemical rockets. While their efficiency allows for continuous acceleration over long periods, the initial acceleration can be slow, which might not be suitable for missions requiring rapid maneuvers or escaping strong gravitational fields. Plasma material interactions also pose a significant concern. The extremely hot and energetic plasma can cause erosion of thruster components, particularly electrodes and grids in some designs, which can limit the operational lifetime of the engine. Developing propulsion-grade, erosion-resistant materials that can withstand these extreme plasma conditions is crucial for long-duration missions. Researchers are exploring various propellants beyond traditional xenon, such as krypton, argon, and even iodine, each with its own advantages and challenges regarding cost, storage, and corrosive properties. Despite these challenges, the advancements in plasma propulsion are undeniable. The ongoing research and development in areas like magnetic confinement, advanced materials, and power electronics are steadily bringing these futuristic engines closer to practical application. The Deep Space Atomic Clock, a miniaturized, ultra-precise mercury-ion atomic clock, launched in 2019, represents a critical step toward enabling spacecraft to navigate independently in deep space, a capability that will be essential for future missions utilizing advanced propulsion systems. Its successor, the Deep Space Atomic Clock, too, is slated to fly on the Veritas mission to Venus in 2028, further demonstrating the evolution of technologies that support long-duration, high-precision space travel. The continuous acceleration capabilities, high fuel efficiency, and potential for significantly reduced travel times offered by plasma propulsion promise to redefine our reach into the cosmos, opening up new frontiers for exploration and potentially even interstellar travel. While plasma propulsion pushes the boundaries of conventional rocketry, the ultimate goal for interstellar travel, and indeed for a truly transformative shift in space exploration, lies in harnessing the power of fusion. Specifically, magneto-inertial fusion, MIF, stands out as a particularly promising candidate for achieving this ambitious objective. MIF is a hybrid approach that ingeniously combines elements of both magnetic confinement fusion, MCF, and inertial confinement fusion, ICF, aiming to leverage the strengths of each while mitigating their individual challenges. At its core, Fusion power replicates the process that fuels stars, merging light atomic nuclei to release immense amounts of energy. This energy release is orders of magnitude greater than chemical reactions, millions of times more per unit mass, making it an incredibly potent energy source for propulsion. The appeal of fusion for space travel is multifaceted. It offers exceptionally high specific impulse, meaning a given amount of fuel can produce thrust for a much longer duration, and it has the potential for significantly reduced travel times across vast cosmic distances. MIF distinguishes itself from other fusion concepts by employing magnetic fields to initially confine a warm, low-density plasma. This preheated, magnetized fuel is then rapidly compressed to fusion conditions by an impulsive driver, often referred to as a liner. This liner can take various forms, including solid metal, liquid metal, or even an imploding shell of plasma jets. The magnetic field plays a crucial role by insulating the hot plasma from the colder liner, preventing rapid heat loss, and allowing the plasma to reach the extreme temperatures and densities required for fusion to occur. This magnetic insulation reduces the implosion speed and instantaneous peak power needed compared to pure inertial confinement fusion, making the technological requirements less daunting. Several specific MIF concepts are under active investigation for propulsion applications. One notable example is the Z-pinch magneto-inertial fusion concept, where a column of gas is compressed to thermonuclear conditions by an estimated axial current of approximately 100 megamperes. The magnetic field generated by this massive current compresses the plasma, and this process is repeated in rapid pulses. Another approach is the fusion-driven rocket, FDR, which forms a magnetized target plasma, often a field-reversed configuration, FRC, and then implodes a metal liner, such as lithium, inductively to trigger fusion. The liner then absorbs the fusion output and becomes the propellant, expanding through a magnetic nozzle to generate thrust. The MAGLIF, magnetized liner inertial fusion, rocket is another variant, where fuel is preheated and axially magnetized before a Z-pinch-driven metal liner implodes it. The resulting pulsed microshots are then directed through a magnetic nozzle for propulsion. Plasmajet magneto-inertial fusion, PJMIF, involves dozens to hundreds of supersonic plasma jets forming a spherical imploding liner around a pre-magnetized target. Each collapse constitutes a fusion pulse, and the resulting plasma can be exhausted for thrust. Companies like Helicity Space are also developing fusion drives based on magneto-inertial fusion, aiming to efficiently convert electricity into plasma heating and directly produce thrust by fusing hydrogen isotopes into helium. The advantages of MIF for space travel are compelling. Its ability to achieve fusion at intermediate densities between those of magnetic confinement and inertial confinement suggests a potentially lower cost and less complex pathway to fusion power. The pulsed nature of many MIF concepts also allows for a standoff design, where the fusion reaction occurs at a distance from the spacecraft's main components, reducing thermal loads and radiation exposure to the engine itself. This also simplifies reactor design compared to steady-state magnetic confinement systems like tokamaks, which must contain extremely hot plasma mere centimeters from delicate hardware. Furthermore, MIF could utilize solid propellants like lithium foils, which have high density, thereby lowering the tankage mass for a given mission. The high specific impulse achievable with fusion propulsion, potentially ranging from 10,000 to 1 million seconds, translates to exhaust velocities that could enable travel to Proxima Centauri in as little as 13 years, a dramatic reduction in transit times compared to current technologies. For missions within our solar system, such as to Mars, fusion drives could cut travel times to a mere 2 months. However, the path to realizing MIF for space propulsion is not without significant challenges. Achieving and maintaining stable fusion reactions in space where experiments have yet to be conducted, remains a primary hurdle. The immense heat and radiation generated by fusion reactions pose substantial engineering problems for spacecraft design and material science. While MIF aims for lower implosion speeds and peak powers than ICF, the technological demands for the pulsed power systems and liners are still considerable. For instance, the Z-pinch concept requires an axial current of approximately 100 mA, and MAG-LIF simulations suggest the need for pulsed power machines producing 45 to 60 mA to achieve high yields. The precise synchronization required for plasma jet-driven concepts, where multiple supersonic plasma jets must converge symmetrically, presents another complex engineering challenge. Another critical aspect is achieving ignition, where the fusion yield equals the energy absorbed by the target. While significant progress has been made in fusion research, achieving net energy gain, where the fusion power output exceeds the power input to the system, is crucial for practical applications, both for terrestrial power generation and space propulsion. For propulsion, even a system with a power amplification, Q, of 1:1, where output equals input, could be useful, but higher gains are desirable for efficient operation. The development of MIF also necessitates robust radiation shielding and structural integrity to withstand the powerful fusion pulses. While fusion rockets may produce less radiation than fission rockets, shielding mass remains a consideration. The economic viability of these systems is also a factor, as the cost of developing and deploying such advanced propulsion technologies will be substantial. However, some studies suggest that MIF's intermediate density approach could lead to a low-cost minimum in the thermonuclear fusion parameter space, potentially reducing overall costs compared to other fusion concepts. Despite these challenges, the potential rewards of successful MIF development are immense. It promises to unlock unprecedented capabilities for deep space exploration, enabling faster and more efficient travel to the outer planets and beyond. Robotic missions to the outer heliosphere and even interstellar flyby missions could become a reality within decades, while crewed missions to the outer planets might be possible in the second half of this century. Furthermore, the development of fusion propulsion could indirectly contribute to Earth's environmental goals by enabling off-world mining and industry, thereby reducing terrestrial resource consumption. The long-term vision for magneto-inertial fusion, with its potential for high single-shot yields and reduced technological complexity compared to other fusion approaches, positions it as a leading contender for the ultimate goal of interstellar travel. Developing advanced propulsion systems for interstellar travel presents a formidable array of challenges that span multiple scientific and engineering disciplines. While the theoretical advantages of technologies like nuclear thermal, nuclear electric, plasma, and magneto-inertial fusion propulsion are clear, translating these concepts into practical, flight-ready systems requires overcoming significant hurdles. One of the most persistent challenges across all advanced propulsion concepts is the need for robust, high-performance materials. For nuclear thermal propulsion, NTP, the degradation of engine components due to extreme heat is a major concern. The outlet temperature of an NTP reactor can reach approximately 3,000 Kelvin, 2,700 Celsius, and currently, no nuclear fuel can operate at such temperatures for the desired duration of a mission. This necessitates the development of new fuel and structural materials that can withstand these intense conditions, including minimizing high-temperature hydrogen corrosion and preventing brittle fracture at low temperatures. Similarly, nuclear electric propulsion (NEP) systems, while operating at lower temperatures than NTP, still require advanced shielding materials, fission fuels, and designs for reliable space-rated reactors. High-temperature thermal management technologies are crucial for NEP, as is the development of radiation-hardened electronics for autonomous operations. Plasma propulsion systems, including those utilizing quasi-neutral plasma, face material science challenges related to plasma-material interactions. Processes like ion-induced sputtering, sputter erosion, and plasma contamination can degrade thruster cavity walls and support structures, potentially leading to system failure. Developing propulsion-grade electrode and grid materials that are resistant to erosion and can withstand extreme plasma conditions is a significant area of research. Advanced materials with complex geometries are being investigated to suppress secondary electron emission and ion sputtering rates, which could lead to longer thruster lifetimes and improved efficiencies. For magneto-inertial fusion, the challenges are even more profound, given its earlier stage of development. These include the need for precise control over plasma instabilities, the ability to rapidly reload and clear the chamber between fusion pulses, and the development of materials that can endure the intense blast debris and radiation from fusion reactions. The sheer energy requirements to initiate and sustain fusion, even with the aid of magnetic fields to relax compression requirements, are substantial. Beyond materials, power generation and management pose another critical hurdle. Advanced electric propulsion systems, whether nuclear electric or plasma-based, demand significant electrical power. For instance, the VX-200 plasma engine requires 200 kilowatts of electrical power to produce 5 in of thrust, highlighting the substantial energy needs. While fission reactors can meet these power requirements, the mass of the reactor, including heat rejection systems, can be prohibitive. Scaling up electric thruster technology from the current low power levels, 1 to 10 kilowatts, to the hundreds of kilowatts required for NEP missions is a major engineering undertaking. Efficiently generating and utilizing large amounts of electrical power while maintaining structural integrity and minimizing energy losses is paramount. This also necessitates advancements in lightweight, high-efficiency power conversion engines and high-temperature thermal management technologies. Effective thermal management is particularly challenging in the vacuum of space, where convective heat transfer is absent, requiring large and efficient radiator systems to dissipate waste heat. Radiation shielding is a universal concern for any nuclear-powered spacecraft, whether for propulsion or power generation. While nuclear propulsion can significantly reduce trip times, thereby lowering crew exposure to cosmic radiation, the engines themselves are powerful sources of radiation. Shielding must protect the crew, sensitive electronics, and cryogenic propellants from gamma rays and neutrons. The design of radiation shields must minimize mass while effectively attenuating radiation, a complex task given the need for active cooling and the potential for radiation streaming through flow channels. Researchers are exploring novel, lightweight shielding materials, including flexible and 3D printable options, to address this challenge. The operational complexities of these systems also present unique challenges. Nuclear thermal engines, for example, do not start and shut down like conventional combustion engines. The rapid increase in temperatures during startup can cause material failures, and the engines take longer to shut down due to heat from nuclear decay, requiring continued cooling. This intricate interplay between thermodynamic and neutronic effects demands sophisticated modeling and control systems. For electric propulsion systems, long-duration operation requires components with stable and extended lifetimes, as well as robust in-orbit autonomous control and fault detection technologies. Finally, the development of advanced propulsion is not solely a technical endeavor. It also faces significant economic and political hurdles. The high initial mass requirements of many advanced propulsion systems, particularly nuclear ones, can lead to increased launch costs. Historically, funding for breakthrough propulsion technologies has been inconsistent, with significant large-scale NASA investment largely absent since the 1970s. Public perception and safety concerns surrounding nuclear reactors and radioactive materials on rockets can also hinder development and deployment, as evidenced by past protests during spacecraft launches carrying plutonium. Overcoming these challenges will require sustained investment, international collaboration, and effective communication to build public trust and support for these transformative technologies. The development and deployment of advanced propulsion systems, particularly those relying on nuclear technologies, introduce a complex array of safety and environmental considerations that demand rigorous attention. A primary concern revolves around the potential for radiological hazards, both during launch and in space. For nuclear thermal propulsion (NTP) and nuclear electric propulsion (NEP) systems, the presence of radioactive materials, such as uranium in reactors or plutonium in radioisotope thermoelectric generators (RTGs), necessitates robust safety protocols. During the launch phase, the risk of an accident leading to the release of radioactive material is a significant public concern. While nuclear reactors for space propulsion are designed to be launched cold, meaning they are not critical and contain no radioactive fission products at launch, the possibility of a launch vehicle failure still exists. In such an unlikely event, command destruct mechanisms are envisioned to ensure debris falls into an ocean, and specialized teams like the Nuclear Emergency Search Team, NEST, are in place for cleanup if land impact were to occur. However, even with these measures, public apprehension is understandable, as evidenced by past protests related to spacecraft carrying plutonium. The environmental impact of rocket launches themselves, even without nuclear materials, includes the creation of ground clouds with exhaust that can interact with ecosystems, leading to localized environmental changes such as acid rain and soil acidification. While the current frequency of launches has a limited impact, an increase in launch rates could lead to more significant effects on biodiversity. Once in space, the safety concerns shift to the operational integrity of these nuclear systems and the management of radioactive waste. For NTP, the reactor would only be started once in orbit, mitigating some launch-related risks. However, the long-term operation of nuclear systems in space raises questions about potential radiation exposure for astronauts and the ultimate disposal of spent nuclear fuel. Astronauts are already exposed to significant radiation from galactic cosmic rays, GCRs, and solar energetic particles, SEPs, during deep space missions, and this exposure is a major health risk, potentially leading to cancer, cardiovascular disease, and cognitive impairment. Reducing transit times through advanced propulsion, such as NTP, could actually decrease overall crew exposure to these natural space radiation hazards. Nevertheless, the nuclear systems themselves contribute to the radiation environment. The disposal of high-level nuclear waste from space reactors presents a unique challenge. While space disposal has been explored as a way to permanently remove radioactive waste from Earth, ensuring its safe and irreversible trajectory away from our planet is paramount. Options like solar orbit or lunar burial have been considered, but they require extremely reliable launch and propulsion systems to prevent accidental return to Earth. The sheer magnitude of nuclear waste generated on Earth makes universal space disposal impractical due to the high launch rates and associated environmental and economic factors. Therefore, space disposal would likely be limited to specific, highly radioactive components. Plasma propulsion, while not relying on nuclear fission or fusion within the thruster itself, still has health and environmental considerations. The high-energy ions used in plasma propulsion could produce radiation, necessitating adequate protection for astronauts. Researchers are also studying the environmental impact of long-term exposure to low levels of expelled particles from these engines. However, plasma propulsion systems often use inert gases or even water as fuel, promising a cleaner alternative to traditional chemical propulsion with significantly reduced emissions during launch. For advanced concepts like magneto-inertial fusion, the safety and environmental profile is generally considered more favorable than fission-based systems. Fusion reactors, unlike fission reactors, cannot experience a runaway chain reaction or a meltdown like those seen in Chernobyl or Fukushima. The fusion process relies on a continuous input of fuel, and any perturbation would cause the reaction to cease immediately. Furthermore, fusion reactors produce no high-activity, long-lived radioactive waste. The burned fuel is inert helium, and while activation products will be generated in the reactor materials by fast neutrons, these are typically classified as very low, or medium activity waste with relatively short half-lives, allowing for recycling within about 100 years. However, challenges remain in understanding and quantifying this source term for fusion, particularly regarding dust and tritium, which are crucial for licensing activities. International regulations play a crucial role in governing the use of nuclear power sources in outer space. The United Nations General Assembly adopted the principles relevant to the use of nuclear power sources in outer space in 1992, which aimed to minimize the quantity of radioactive material in space and restrict the use of nuclear power sources to missions that cannot reasonably be operated by non-nuclear energy sources. These principles emphasize thorough safety assessments, including probabilistic risk analysis, to reduce the risk of accidental exposure to harmful radiation. National Security Presidential Memorandum 20, NSBM 20, in the U.S. also establishes safety guidelines and risk assessment requirements for launching space vehicles with nuclear systems. Public perception remains a significant hurdle for nuclear propulsion. The word nuclear often evokes associations with weapons of mass destruction, leading to public opposition despite the potential benefits for space exploration. However, recent surveys indicate a growing public favorability towards nuclear energy, with a significant portion of the U.S. public supporting its use and even the construction of new nuclear power plants. This shift in opinion may be influenced by concerns about climate change and the recognition of nuclear power as a carbon-free energy source. Effective and honest communication about nuclear safety will be critical to building public trust and support for these transformative technologies. Overcoming these challenges will require sustained investment, international collaboration, and effective communication to build public trust and support for these transformative technologies. The economic impact of faster space travel is nothing short of transformative, promising to reshape global industries, create new markets, and drive unprecedented growth. The space economy is already booming, reaching an estimated $570 billion in 2023, a 7.4% increase from the previous year, and projections suggest it could reach an astounding $1.8 trillion by 2035. This growth isn't just about rockets and satellites. It's about the ripple effect across numerous sectors on Earth. One of the most immediate and significant economic benefits of faster space travel is the drastic reduction in launch costs. Companies like SpaceX have already demonstrated the value of reusable launch systems, significantly lowering the financial barrier to accessing space. As propulsion technologies advance, further cost reductions will make space even more accessible, opening the market to a wider array of participants and fostering a more scalable and commercially viable ecosystem. This accessibility will enable the deployment of more satellites, supporting expanded global communication networks, improved weather forecasting, and enhanced geospatial intelligence, all of which have substantial economic value on Earth. Faster space travel will also accelerate the development of critical space infrastructure. Lower-cost access to orbit makes it easier to build and expand this infrastructure, which in turn enables more services and supports more durable business models. This includes everything from in-orbit servicing and manufacturing to the construction of space habitats. The ability to transport materials and personnel more quickly and efficiently will be crucial for establishing and maintaining these complex undertakings. For instance, 3D printing in orbit, leveraging microgravity, could enable the production of fiber optic cables, tools, and construction materials in new, more effective ways, further reducing dependence on Earth-based manufacturing and speeding up construction timelines for deep space missions. The advent of faster space travel will undoubtedly supercharge the burgeoning space tourism industry. This luxury market, pioneered by companies like Virgin Galactic and SpaceX, is projected to become a multi-billion-dollar industry, potentially exceeding $800 billion by 2030. While orbital flights are currently expensive, with tickets allegedly costing tens of millions of dollars, increased competition and technological advancements are expected to lower these costs, eventually making space travel more affordable and accessible to a broader demographic. This will not only generate significant revenue, but also create numerous jobs in aerospace, hospitality, and related industries. Beyond tourism, faster space travel unlocks the immense potential of resource extraction from celestial bodies. Asteroid mining, for example, could provide access to valuable materials like platinum, gold, and rare earth elements, which are becoming increasingly scarce on Earth. The asteroid belt alone is estimated to contain quadrillions of dollars worth of minerals. While the logistics are complex and expensive, the long-term economic benefits could be staggering, potentially disrupting terrestrial resource markets and reducing reliance on environmentally impactful mining practices on Earth. For instance, a single shipment of space minerals could devalue gold by 50%, and platinum-producing nations could see significant impacts. Moreover, water ice extracted from asteroids and the Moon could be converted into rocket fuel, creating gas stations in space that would significantly reduce the cost and increase the feasibility of deep space missions. Lunar and Martian colonization also become far more economically viable with faster transit times. The ability to transport supplies, crews, and equipment more rapidly reduces the logistical burden and overall cost of establishing and sustaining off-world settlements. While traditional approaches to lunar colonization estimate trillions of dollars, innovative architectures, coupled with reduced launch costs, could bring the development cost of a 1,000-person lunar colony down to a few billion dollars, with annual support costs around $1 billion. On Mars, the availability of resources like deuterium for fusion reactors, which is 5 times more common than on Earth, could power a robust Martian economy. Furthermore, the unique positional advantage of Mars could allow it to act as a keystone for extractive activities in the asteroid belt. Martian colonies are also envisioned as pressure cookers for invention, with innovations licensed back to Earth, raising living standards and contributing substantial income to the colony's development. The economic impact extends to job creation across a wide spectrum of disciplines. The space industry is a significant employer, supporting hundreds of thousands of jobs globally, from engineers and scientists to technicians and support staff. NASA alone sustained nearly 340,000 jobs across the United States in fiscal year 2021, generating billions in economic output and tax revenues. These are often high-paying, skilled positions, and the growth rate of the global space workforce is estimated at 5 to 10% annually. Faster space travel will only amplify this trend, creating new roles in advanced propulsion development, in-space manufacturing, resource extraction, and space tourism. Moreover, the technological advancements spurred by the pursuit of faster space travel have significant spin-off benefits for Earth-based industries. Innovations developed for space missions often find applications in fields such as health and medicine, transportation, public safety, consumer goods, energy, and information technology. For example, advancements in materials science, robotics, and telecommunications developed for space have found applications in automotive, manufacturing, and mobile communications industries. Space-based technologies also provide invaluable data for climate change monitoring, disaster management, and environmental protection, offering incalculable value to the global economy and society. The economic growth generated by space exploration is a powerful catalyst, fostering industry growth and stimulating job creation in related fields. However, the economic landscape of faster space travel is not without its challenges. The initial capital investments for advanced propulsion systems and space infrastructure are substantial. While reusable rockets have dramatically reduced launch costs, further innovation is needed to make deep space travel truly affordable. Regulatory frameworks, safety considerations, and technological hurdles continue to be addressed as the industry matures. There are also concerns about potential wealth inequality if the benefits of space-based resources and opportunities are not distributed equitably. The disruption of terrestrial industries, such as mining, due to the influx of space-derived resources, would need careful management to mitigate negative impacts on mining-dependent countries and their workforces. Despite these challenges, the overwhelming consensus is that the economic benefits of faster space travel will be profound. It represents a shift from space as a state-led frontier to a commercially supported economy, with private investment playing a crucial role in driving innovation and growth. Public-private partnerships are essential for maximizing research and development, linking the private sector to public sources of financial and intellectual capital. The continued investment in space exploration not only drives technological advancement, but also provides significant economic returns, positioning nations at the forefront of global innovation and economic development. The ability to travel faster and more efficiently through space will unlock new markets, create countless jobs, and provide solutions to some of Earth's most pressing problems, ultimately leading to a more prosperous and technologically advanced future for humanity. The allure of interstellar travel, the dream of voyaging to distant star systems, has captivated humanity for generations. While our current technological capabilities make such journeys seem like the stuff of science fiction, ongoing research and conceptual designs are steadily bringing this dream closer to reality. The sheer scale of the universe presents the most formidable challenge. Our nearest star system, Alpha Centauri, is approximately 4.37 light-years away, or about 25 trillion miles. Even with our fastest current spacecraft, reaching Alpha Centauri would take tens of thousands of years. This immense distance necessitates revolutionary propulsion systems that can achieve a significant fraction of the speed of light. One of the most ambitious and detailed early studies for an interstellar probe was Project Daedalus, conducted by the British Interplanetary Society between 1973 and 1978. This project aimed to design an uncrewed spacecraft capable of reaching Barnard's star, 5.9 light-years away, within a human lifetime, specifically a 50-year flight time. The proposed Daedalus spacecraft, with an initial mass of 54,000 tons, including 50,000 tons of fuel, was envisioned as a two-stage fusion rocket. The first stage would accelerate the spacecraft to 7.1% of the speed of light, and the second stage would boost it to about 12% of the speed of light, followed by a 46-year cruise. The Daedalus design, though decades old, remains a testament to the ingenuity applied to the problem of interstellar travel, with its core concept holding up remarkably well. A follow-up, Project Icarus, began in 2010 to re-examine the Daedalus design in light of modern technological advancements. Beyond fusion rockets, other theoretical propulsion systems offer even more tantalizing prospects. The Bussard ramjet, proposed by physicist Robert W. Bussard in 1960, is a theoretical fusion rocket variant that would scoop up hydrogen from the interstellar medium using a massive magnetic field, compress it, and then use thermonuclear fusion to generate thrust. In principle, such a ramjet could accelerate continuously, potentially reaching velocities arbitrarily close to the speed of light. The faster it travels, the more fuel it collects, creating a self-sustaining acceleration. While the concept is elegant, the incredibly tenuous density of the interstellar medium, about 1 atom per cubic centimeter, and the enormous power required for the magnetic field pose significant challenges. However, some variations suggest using lasers or microwaves to add energy to the incoming hydrogen stream, potentially increasing the exhaust velocity. Looking further into the future, concepts like warp drives and wormholes move from the realm of hard science fiction into speculative theoretical physics. The warp drive, popularized by Star Trek, proposes to achieve faster-than-light travel by manipulating space-time itself. Theoretical physicist Miguel Alcubierre, in 1994, devised a solution to Einstein's field equations that describes a warp bubble around a spacecraft. This bubble would contract space in front of the ship and expand it behind, effectively moving the spacecraft without the vessel itself exceeding the speed of light locally. While mathematically consistent with general relativity, the Alcubierre drive currently requires exotic matter with negative energy density, which has not been observed and may not even exist. Even if it could exist, the immense amount of energy required, equivalent to converting the entire mass of Jupiter into energy, makes it currently impossible. Wormholes, also a staple of science fiction, are hypothetical tunnels through space-time that could connect widely separated points, potentially allowing for near-instantaneous travel across vast cosmic distances. While consistent with Einstein's theory of general relativity, traversable wormholes are highly speculative. The primary challenges include their inherent instability. They tend to collapse almost immediately, and stabilizing them would require exotic matter with negative energy density. Furthermore, even if stable, the tidal forces within a wormhole could be severe enough to tear a traveler apart. As of now, there is no experimental evidence or astronomical observation confirming the existence of wormholes. Despite these incredible theoretical concepts, humanity has already taken its first tentative steps into interstellar space. The Voyager 1 and Voyager 2 probes, launched in 1977, have both crossed the heliopause and are now operating in interstellar space, sending back valuable data about the interstellar medium. Pioneer 10 and 11, launched in the early 1970s, are also on interstellar trajectories. These missions, while not designed for rapid interstellar transit, demonstrate our ability to send instruments beyond our solar system. Future proposed missions, like NASA's Interstellar Probe, aim to specifically explore and characterize the heliosphere and interstellar space, with a potential launch between 2036 and 2041. This probe is designed to travel at speeds of about 6 to 7 astronomical units per year, leaving the heliosphere in approximately 16 years. Another promising avenue for relatively near-term interstellar exploration is beam-powered propulsion, particularly laser sails. The Breakthrough Starshot initiative, co-founded by Yuri Milner, Stephen Hawking, and Mark Zuckerberg in 2016, proposes sending a fleet of ultralight nanocrafts, equipped with light sails, to the Alpha Centauri system. These nanocrafts would be propelled by powerful ground-based lasers, accelerating them to speeds between 15% and 20% of the speed of light. At such speeds, a flyby mission to Alpha Centauri could take just over 20 years, with data transmitted back to Earth in approximately 4 years. While the project faces significant engineering challenges, it offers a credible pathway for direct interstellar spacecraft exploration within the coming decades. Electron beams have also been proposed as a propulsion method, potentially offering a greater range and ability to propel heavier spacecraft compared to laser sails. The challenges of interstellar travel extend beyond propulsion. At relativistic speeds, collisions with even tiny interstellar dust particles could cause catastrophic damage to a spacecraft. Effective shielding methods will be crucial. Long-duration missions also necessitate robust life support systems, especially for crewed missions, and reliable communication over vast distances, which will inherently involve significant time delays. Autonomous systems will be essential for deep space missions due to these communication delays, enabling probes to navigate, collect data, and even perform self-repairs without constant human intervention. The future of interstellar travel will likely unfold in stages, beginning with uncrewed probes utilizing advanced propulsion systems like nuclear thermal, nuclear electric, and fusion drives, as well as laser sails. As our understanding of physics and engineering progresses, more exotic concepts like warp drives and traversable wormholes might transition from theoretical constructs to tangible possibilities. However, the ethical implications of such journeys are paramount. Considerations include planetary protection, ensuring we do not contaminate potential extraterrestrial environments, and the ethical responsibilities associated with encountering, or even colonizing, other worlds. The very act of expanding humanity's reach into the cosmos demands a profound commitment to responsible exploration, environmental stewardship, and respect for any potential extraterrestrial life. This blend of scientific ambition and ethical foresight will shape humanity's destiny among the stars, ensuring that our interstellar aspirations reflect the best of human values. The journey to the stars, propelled by advanced propulsion systems, transcends mere technological prowess. It forces humanity to confront profound ethical considerations and the intrinsic vulnerabilities of the human factor. As we push the boundaries of exploration, the moral compass guiding our decisions becomes as crucial as the scientific principles underpinning our engines. One of the foremost ethical considerations revolves around the well-being of the astronauts themselves. Long-duration missions, particularly those venturing beyond Earth's protective magnetosphere, expose individuals to unprecedented psychological and physiological stressors. The isolation and confinement of deep space can lead to a range of mental health challenges, including anxiety, depression, sleep disturbances, and even cognitive impairments. Astronauts are highly trained, but they are still human, and the psychological toll of being millions of miles from home, with limited social interaction and communication delays with Earth, cannot be underestimated. Ethical frameworks must prioritize robust psychological support systems, both pre-mission and in-flight, including access to mental health professionals and innovative countermeasures like virtual reality interfaces that can simulate Earth-like environments or facilitate virtual visits with loved ones. The balance between an astronaut's right to privacy and the necessity of continuous mental health monitoring for mission success presents a delicate ethical dilemma that requires careful consideration and transparent informed consent. Furthermore, the physiological impacts of microgravity, radiation exposure, and altered circadian rhythms demand extensive research and the development of effective countermeasures to ensure the long-term health of space travelers. Ethical guidelines must ensure that scientific ambition does not compromise astronaut safety and well-being. Beyond the individual astronaut, the ethical implications extend to the very environments we explore. Planetary protection protocols are already in place to prevent forward contamination, the accidental introduction of Earth microbes to other celestial bodies, and backward contamination, the potential return of extraterrestrial life that could pose a threat to Earth. With faster propulsion, the risk of such contamination, both intentional and unintentional, could increase. Ethical foresight demands a commitment to preserving the pristine nature of extraterrestrial environments, recognizing their intrinsic value and the potential for unique, undiscovered ecosystems. This includes establishing clear guidelines for responsible exploration, minimizing human impact, and implementing strict protocols to protect any potential extraterrestrial life, even microbial. The discovery of any form of extraterrestrial life would raise profound ethical questions about our moral obligations towards it, with some arguing for strong protection of all extraterrestrial life and environments. The potential for encountering intelligent extraterrestrial life introduces an entirely new layer of ethical complexity. How should humanity prepare for such an encounter? What language or method of communication should be used? Ensuring peaceful and respectful interaction is paramount, requiring careful consideration of potential cultural and ethical differences that may exist between our species and an alien civilization. The anthropocentric view, which often places humans as morally superior, is challenged by the possibility of encountering civilizations that may be technologically or ethically more advanced. Ethical frameworks must guide our response strategy, emphasizing universalist ethics where all sentient beings are valued equally. The governance of space resources also presents significant ethical challenges. As humanity ventures further, the prospect of mining asteroids or other celestial bodies for valuable resources becomes increasingly feasible. Without clear international agreements and ethical frameworks, this could lead to conflicts over resource ownership and exploitation, benefiting a few at the expense of many or the celestial bodies themselves. International cooperation and the establishment of a robust governance framework, such as those being developed by the Hague International Space Resources Governance Working Group, are crucial to ensure equitable access and sustainable use of these resources for the benefit of all humankind. Ethical principles of space preservation, conservation, and sustainability advocate for valuing the solar system for its own sake, avoiding exploitation, and leaving celestial bodies no worse than we found them. Finally, the human factor extends to the societal impact on Earth. Faster space travel and the expansion into the cosmos could inspire new generations, drive technological advancements, and foster a sense of global unity through shared ambition. However, it also raises questions about resource allocation, whether investments in space exploration could be better utilized to address pressing issues on Earth such as poverty, climate change, or healthcare. Moreover, the high costs associated with advanced space travel could exacerbate social inequalities, limiting access to space opportunities to an elite few. Ethical considerations demand that opportunities for space travel be equitable and inclusive, reflecting the diversity of humanity. The overview effect, the profound cognitive shift experienced by astronauts viewing Earth from space, has often instilled a powerful sense of environmental stewardship and global interconnectedness. This perspective can reinforce the ethical imperative to protect our home planet, while simultaneously inspiring responsible exploration of the cosmos. Ultimately, the development of advanced propulsion systems and the dream of interstellar travel compel us to reflect on what it means to be human in the vastness of the universe. It demands a proactive approach to ethical dilemmas, ensuring that our technological progress is matched by a profound sense of moral responsibility. This blend of scientific ambition and ethical foresight will shape humanity's destiny among the stars, ensuring that our interstellar aspirations reflect the best of human values.